Obtain the mesh file and also the full training movie by purchasing this product. One of the disadvantages of frozen gasoline fuel is when the temperature drops during cold seasons or in cold places. When the gasoline temperature drops, sediments are removed first, then heavy hydrocarbon molecules begin to freeze and continue to mummify as temperatures continue to decrease. To prevent freezing of gasoline, it is necessary to raise the temperature of the gasoline in the fuel storage tanks. One way to increase the temperature of the gasoline fuel in the fuel tank is to use pipes carrying the hot fluid flow. The use of helical tubes in situations where space constraints are due to greater heat transfer in a given space is of particular interest. Gasoline is not a pure substance and consists of several hydrocarbons and additives such as ethanol, hexane, heptane, and so on. Since most of the gasoline have a unique chemical structure called isomers, the solidification and melting point of each of these materials are different. This inner tube carries a flow of water at a temperature higher than the temperature The present issue concerns the simulation of a gasoline fuel tank carrying a single-way reciprocating spiral tube passing through the tank. The inner tube carries a flow of water at a temperature higher than the temperature of the gasoline to increase the fuel temperature by creating heat transfer between the diesel and the water and thus prevent freezing inside the tank. Therefore, the present model uses a solidification and melting module for the simulation. We designed the three-dimensional geometry of the model using Design Modeler software. The model consists of two main parts, including a fuel tank and the spiral inner tube for hot water flow. To mesh the present model, we have used ANSYS meshing software, and the mesh type is unstructured. So the inner tube uses a finer grid. In the viscose model, the standard K-Epsilon model has been used. That is a two-equation turbulence model that allow the determination of both a turbulent length and time scale by solving two separate transport equations. The standard K-Epsilon model is in ANSYS Fluent, falls within this class of models and has become the workhorse of practical engineering flow calculations in the time since it was proposed. Robustness, economy, and reasonable accuracy for a wide range of turbulence flows explain its popularity in industrial flow and heat transfer simulations. Also, it is a semi-empirical model. The standard K-Epsilon model is a model based on model transport equations for the turbulence kinetic energy, K, and its dissipation rate, epsilon. The model transport equation for K is derived from the exact equation, while the model transport equation for epsilon was obtained using physical reasoning in the derivation of the K-Epsilon model. The assumption is that the flow is fully turbulent and the effect of molecular viscosity are negligible. The standard K-Epsilon model is therefore valid only for fully turbulent flows. So we click on solidification and melting button and also define a Moshe zone constant. That the Moshe zone constant measures the amplitude of the damping. The higher this value, the steeper the transition of the velocity of the material to zero as it solidifies. Very large values may cause the solution to oscillate. The liquid water exists in the part helix. The material of the helix wall is copper. Mass flow inlet boundary condition has been chosen for the inlet boundary condition, and also the mass flow rate is specified in this section. As previously mentioned, the pressure-based solver allows you to solve your flow problem in either a segregated or coupled manner. Using the coupled approach offers some advantages over the non-coupled or segregated approach like simple or simple C. The coupled scheme obtains a robust and efficient single-phase implementation for steady-state flows with superior performance compared to the segregated solution schemes. This pressure-based coupled algorithm offers an alternative to the density-based and pressure-based segregated algorithm with simple type pressure-velocity coupling. For transient flows, using the coupled algorithm is necessary when the quality of the mesh is poor or if large time steps are used. The coupled algorithm solves the momentum and pressure-based continuity equation together. The standard initialization method has been used for this CFD simulation. And from the solidification and melting liquid fraction two-dimensional contour, we can easily see that the melting is happening, and some part of the gas line that was completely solid start to melt and change to the liquid phase. At the end of the solution, and when the simulation is completely done, the liquid fraction of the tank will be equal to 1. A summary of the defining steps materials of the problem or PCMs are materials with organic compounds that can absorb and store a large amount of latent heat energy. Obtain the mesh file and also the full training movie by purchasing this product. To benefit from Master CFD services including simulation, consultation and training, contact our experts via info@mastercfd.com.